We'll be continuing with the section on formatting and accessibility, and for this we'll be focusing on the accessibility part for in Matplotlib. That's basically making plots more accessible to for things like color blindness and dyslexia and age-related farsightedness, things like that. So let's start with fonts. Before we continue, I just want to give you a heads up. You should go ahead and get your little demo codes from last time loaded up and ready to go, because we will start doing another tiny mini exercise in a couple of slides. So anyway, let's talk about fonts and font sizes. So you can set the text base class and all derivatives, titles, legends, all of that stuff to have a particular font size. You can also pick the font family, so that's like serif or sans serif and different more. And you can also pick fonts like Helvetica and Arial and things like that. One of the things that you have to keep in mind when you're doing this is that most journals will set a hard minimum font size of 9 to 10 points. And that's not just the axis labels and tick labels. That's also like any little annotations inside your plot. So if you have to squeeze in all these little tiny labels of ellipses or points in a very crowded map, you're still going to get dinged. I'm speaking from personal experience on this. That in mind, you should still prefer 11 to 14 point fonts, and in general, you should err larger for older readers. It's because when you're going through the peer review process, it's a lot of the times the senior readers that sort of determine the trajectory of your plots, and you want to be on their good side, you know. Also, it's just easier for everyone if you can if the fonts are large enough to read comfortably. Also, you want to pick a common style or something very similar to a common style and just stick with it. There's no consensus whether serif or sans serif fonts are more legible. You'll find research online going both ways. Most of the reports will say that their findings favor this particular font style or that particular font style, but unfortunately they're split. So you'll have the serif camp that says the research supports them, and the sans camp that says the research supports them, and neither one is actually right. So it seems to be that those that have actually done meta-analyses on the topic have they say that whether for the average reader or even if you're concerned with things like dyslexia, what matters most is familiarity. So whatever font size your local area or your local culture is, and or the academic circles that you move in, whatever their preferred font sizes or font types and styles are, that's what you should stick with. And you can do that. You can do that at the top level. You can do that at the level of individual plots. It's up to you. The way you can do that, should you match it with text font as well? Good question. In general, what you have to match for your font or for text is the symbols. So if you have like a serif M with an O dot or something as a subscript as a symbol in your text, you want that to show up in your plot. But math text will do that for you. There are ways to set math text to serif or sans serif using font families and RC parameters. So like if you import Matplotlib as in MPL, for instance, then you can call matplotlib.rc, which is a dictionary, and select font or text, and then enter a sort of sub-dictionary for to select the font families or to select individual font styles. Now, you should not use this use text command unless you want to ensure italicized serif math text and you have very obscure math text LaTeX symbols to typeset. Because although it can help with very obscure symbols, one thing that it can do is that it can cause if you haven't installed your own LaTeX distribution, that can throw an error, and you'll have to install a more extended LaTeX software. And if you do have LaTeX installed, it might clash a little bit with the LaTeX that's in your Matplotlib installation. I mean, normally if you have something like Conda, that will manage your math text so that it matches your local LaTeX distribution, but you do have to be careful of that. As far as whether the rest of the text, like the axis tick labels, have to be serif if the text of your journal is serif, I would say no. It's just a matter of being consistent from plot to plot. Personally, I actually prefer sans serif because if you have to make the text small, the serifs can blend a bit, and that can make it harder to read. But that's just my personal preference. So if you want to set the font size at the global level, you can call plot.rcParams. No, sorry, MPL. There's a typo there. You can call matplotlib.rcParams and select and put in brackets the font.size. So that's a dictionary entry. So rcParams is basically a nested dictionary of the parameter settings that format your various settings that format your plots, like the fonts and the default color cycles, the axis tick styles, all of that stuff. So if you set plot.rcParams font size equals 14, that sets all the labels to size 14. Sorry, this is right. It's matplotlib.rcParams.update. This is how you restore defaults. So you can matplotlib.rcParams.update, and then in parentheses, matplotlib.rcParams default. So now let's have you guys return to the plotting code that you've been using during the lectures for the past several Now You Try exercises. I want you to try increasing the font sizes of just the X and Y axes labels to size 14. And one way you can do that is that a lot of functions that instantiate or that modify text or set text in your plots have a font size quark. So, like I said, you just have to set font size equals 14. That's if you want to control only the axis labels at the time. If you wanted to control everything all at once, it's this plot.rcParams font size, and that sets the all label text to 14. So can everyone see this spider screen? Yes, cool. All right. So right now it looks like this. You see these tiny little labels. Any difference between size and font size? For plot, size is the size of the markers.
Okay, but it says in the documentation you can use size or font size. I was just wondering if there's any difference.
Okay, then I was thinking of scatter then. If the documentation says that you can use either, then you can use either.
Okay, so no difference. Thanks.
All right, so this is what it looks like before I've set rcParams. So let's do plot.rcParams, brackets, font.size. Shoot, what did I just do? Font.size equals 14. And then if I run this now, all the text labels are much bigger. And that includes the legend, which is for this size plot, that's maybe not something you want. So it's but it is an option and it may help. So it is worth noting that if you use the plot.rcParams option, it will continue to hang around even if you re-execute the code. So then you actually do have to, if you don't want that anymore, then you actually have to do this. So you have to do the restore the default, like so. And now you've got the tiny text back. So I'm going to put the size equals 14, and just copy, copy, copy. There. Now I've got the result that was in the slides back. All right. So now let's talk about color palettes. This is the big one for talking about things to do with color blindness. So why should you care about that? Well, color blindness affects about 1 in 12 people with one X chromosome and about 1 in 200 people with at least 2 X chromosomes. So it's not exactly rare. And it just helps to try and make plots more colorblind friendly. Generally, it helps everyone, generally whatever you do to help with them, it also can help other people. Because it's not just that there's not just color blindness, there's also color weakness, where part of the where people are missing part of their color receptors for a particular range of colors, and then color contrast may be more muted, and that's even more common. So there are a lot of ways there are a lot of online simulators that you can use to check whether your plots are colorblind friendly. I like this Dalton lens because it lets you check. It doesn't just let you. It doesn't just let you check the image and upload a file. It lets you check different models of color blindness, so that because there's a lot of individual variations, so you may not be able to rely on the results of just one model. So like you can go to so red blind and green blind look fairly similar. And then you can go to different models, like Coblas version 2, for instance. And then you can also read about the methods up here. So shades of blue and orange are the ones that are most easily distinguished for all 3 types of dichromacy. That means missing one color receptor. And the best third color that I found is either gray or cyan. But of course, I'm trusting simulators on this. I am not dichromatic. So I would like to be able to talk to people who have this and see how accurate these are. You can import Tableau's colorblind 10 color palette with this plot.style.use command. There are a lot of color palettes that you can import this way. Tableau colorblind 10 is one that was specifically designed for colorblind people in mind. And we'll talk a bit more about styles later on in this course, in the last lecture block. You can also use plot.colormaps and select a built-in color map, and then you can use this linspace function to generate an in-color palette from an existing color map. And that works well because that means that no two colors that you select will have the same value, which means that even that you could print your plot in black and white and you would still get the same dynamic range. So this is the default color palette. It was designed with colorblind people in mind. It's okay. I've marked, it's not great for more than 4 colors. I've marked some of these cells with question marks because having looked at them with the Dalton Lens program, I've found that some of the methods of simulating color blindness produce ambiguities with these that have question marks, and pretty much all of them get olive confused with something. So avoid olive and possibly avoid these other 3 that have question marks on them. But in any case, you should be varying the marker and line styles for if you have more than 4 data sets on the plot anyway. Well, you should be varying marker and line styles for multiple data sets to begin with. So now let's talk about color maps more generally. Matplotlib docs documentation mostly covers this in the article about choosing color maps. But in short, you need to consider your data type requirements. So should your color map be sequential, diverging, that means sort of dark at both ends and light in the middle, or vice versa. Whether it needs to be cyclical. I've never seen a use for cyclical color palettes, to be honest. Or are your data categorical and you just need like discrete colors? Also, you need to consider the dynamic range. So like how much contrast do you need between the lights and the darks and the colors in between? Or how much contrast do you need over the entire range and between each individual color if you have discrete colors? And you should also consider monotonicity, because this is what determines whether or not your plot is still good in black and white. So you have to ask if does the brightness of your plot vary smoothly and linearly so that it still reads correctly in black and white or reduced color printing. You should also note that all color maps can be reversed in order by just appending this _R to the name of the color map in the string, or as a string. So if you have a color map called Magma is my personal favorite. If you want to reverse the order of that, you just put in the string quotation marks, you put Magma _R. And these are the list of perceptually uniform sequential color maps. So these are the maps that are that were designed to vary uniformly in brightness so that they render just as well in grayscale. If you need more than these, there are also some decent. There are also a few decent close approximations like gray and bone and binary. The rest are not so good. And there are 2 rather infamous offenders that people really liked because they're brightly colored, but and have a lot of dynamic range, but they are awful in terms of perceptual uniformity. So rainbow and jet, avoid those. So, and if you're not familiar with the names, rainbow looks like your classic rainbow spectrum, and jet is very similar, but it adds an extension with like dark gray on one end and I think white on the other end. And so it's basically rainbow with extensions. As for diverging color maps, the ones I've circled are the ones that work out pretty well, and work out well in simulations in color blindness simulations. So I was kind of surprised at the pink, yellow, green, but it is what it is. The rest are pretty much what you would expect. Red, blue works fairly well. Red, yellow, blue works fairly well. Cool, warm works fairly well. Red, yellow, green does not work well. If you're red, green, red, green color blindness makes this basically useless. And spectral is a bit weird because you would think it would work well, but it actually turns kind of red at the end. And in general, you want to avoid. You also want to avoid diverging color maps that have a drastic difference between the two sides in terms of brightness. So now let's have you try. Go back to your miniature exercise plotting code and change the color map for the image to magma. When you're done, the image part should look like this. Good question about the R with the strings with R when setting a label, even if it's not Greek letters. Regarding the LaTeX, it doesn't hurt anything if you do, but if you include the R, so I usually include the R to be on the safe side for anything that's typeset with LaTeX. But usually you don't have to include that. I'm sort of in the habit of doing it from the time when it was pretty much required to make it work. So because math text used to be a lot more limited. How do we judge the lightness? Just by look or similars, or can you get a value somewhere? So the documentation for for color maps. Okay, let me find the choosing color maps documentation. Choosing color maps in Matplotlib. This is a really handy reference to have. So this has a full reference of for the brightnesses of all of these color maps. So you can see how a lot of the sequential ones that I did not highlight have turnover at the light end or wiggle around a lot in this plot space. So the way that you set the color map is literally just this. CMap equals, I selected magma, so there's magma and comma, and there we go. So this is what the magma color scheme looks like. And another decent one that I don't care for as much because it doesn't have as much dynamic range is plasma. That looks like this. This one's good if you need to label stuff in black on top of the color map. And then I can show you the not so good one that looks like that. So a lot of people like this one, but it's not good because it's diverging and not very smoothly. So you can almost kind of see in if you have a large enough monitor, you can actually see that there's a little bit of a bright spot down here in the blue section. Or maybe it's just me. But anyway, so let me change this back to magma. And if you want to reverse the color, it's like that. So that's the little underscore R. And now the light side is at the bottom and the dark is at the top. Now, not all color maps go from dark to light. Some of them actually do go from light to dark, so do pay attention to the reference. Or you can just test it out and see. It's easy enough to change. Right. Most plots now have a CMAP quark if it makes sense to have one. And they pretty much all accept color map names as strings. Older versions of Matplotlib, however, and other color-related functions may require you to import matplotlib.colors and then select the color map from matplotlib.colors, like a dictionary entry. So you'll see that in certain things to do with like selecting colors from a color map to make a custom in-color color palette. That requires knowing this matplotlib.colors. Now let's talk about markers. Easily confused. There are some easily confused shapes. The big two that I find are the big circles and the octagons at the typical sizes that they will appear in plots. These are very difficult to tell apart. So don't use these two together unless they are drastically different color. And generally pick one or the other and skip it entirely. There are other good options. The two hexagons can also be kind of difficult to tell apart, particularly for people with dyslexia. Rotations can be troublesome if the shape is relatively symmetric. So anecdotally, what I understand is that triangles aren't that bad. So typically, if you're going to use shapes that are essentially repeated but rotated relative to each other, prefer the triangles. And if you have to involve any of the others, make sure that they're a very different color to like. And by that, I mean also a very different value so that they read different even in black and white. Also keep in mind this plus sign here. Those can be confused for error bars without caps. And we'll talk about error bars very shortly. So you'll see what caps mean. And I almost guarantee you that you all have actually seen what the caps mean. So so it's just, you'll know what I'm talking about when you see it. Also, these straight line markers that look like the pipe operator or the M dash, those you generally want to avoid because they're kind of hard to see at the typical sizes that they appear, and also they're typically reserved for specialty plots. So the event plot that shows up in the documentation of plot types, and also rug plots. So if you don't know what a rug plot is, it's basically if you have a probability distribution, you'll probably see a curve, and then some people like to put these vertical dashes along the bottom x-axis so you can see where along the x-axis the individual data points landed. So it looks like a shag carpet, basically, under your curve. That's a rug plot. And that's what we typically reserve these vertical pipe marks for, those in event plots. So now time to go right back to your coding plot, our little demo code. And I want you to add markers. So add markers to add circular markers to the blue curve, cosine curve, and diamonds or rhombuses for the exponential curve. All you should have to do is add a shape code to each of the little format strings. It is possible to set the marker separately with the marker quark, if, for instance, you have a non-standard color. But for this type of plot, you can just insert it into the format string. So here's the markers if you need that. Stick that in the chat. Well, basically, this is what it looks like here. So in the format string, before you had a B and a dash, and then anywhere in this string, you could insert a lowercase letter O for the small circles, and similarly with the red dashed line to insert the diamond marker, you put a lowercase d. Almost anywhere on this format string, except you don't want to break up these dashes. So if you had a dash dot curved, you also wouldn't want to put the marker or color letter specifier between the dash and the dot. I'm going to show you another thing that's real quick. So let's say you wanted to turn this a different shade, like let's say you wanted to turn this a different color. So then you would want to, if you wanted to use a non-standard color, then you can't use the format string. So then you have to specify the marker, line style, and color separately. And to do that, you would do, in this case, you have line color and marker color are separate. So you can actually do, so let's see, line style. I have that as a solid line. So there's a dash. Oh, right, it's marker edge color and marker face color because you can set all three of those separately. So marker edge color, let's say that's red. And then marker face color, let's set that as, just to be extra crazy, let's set that as tab pink. That way you can see all three of them. There we go. So now, after all of this, the line is orange, the outline of the marker is red, and the fill color of the marker is pink. So you can set all three of those separately. If you don't choose anything else like the color, then it just defaults, the whole thing is orange. And now this isn't an exercise. I just want to, this is something where I want you to sort of vote in the chat. So, so I want everyone to just take a moment to rank what they think is the order of importance for these lines. So if you think like if you thought the most important curve, so if you plotted all four of these curves on the same plot, imagine what do you think is the most important, which line do you think would look the most important, rank that first, and then go, arrange them in order of most to least important in the chat. So like if you thought the dash dot line was the most important, put that as like the dash and a period first and comma and whatever the next important one is, maybe the dash dash, put that in the comment. So I want to see your feedback here in the meeting chat. I just realized that I think everyone can see everyone else's, so this might not be the most unbiased random survey. I think that's I think that kind of gets the point across. Almost everyone said that solid would read as the most important line, and most people said that the dotted line would read as the least important, with some variability. And actually, I found it interesting that, and kind of as expected, there was some mixture with the dashed and dash dot. But anyway, this is something that you have to sort of consider for your narrative. So most people will read the thickest, solidest line as the most important curve, And most people will read the dotted line as the least important because it tends to be, it's the easiest to sort of lose among the other data. And if you squint at it, it looks the lightest. Now you can adjust the dash and dot spacing. I'm not going to go into that, how to do that right now, but that is something that you can modulate if you need more line styles, or if you, if for some reason you want to make it more clear whether dashed or dash dot is more or less important. But the order is a little bit subject to change, but in general, the solidest line is going to read as the most important, and the most dotted or scattered looking line is going to look the least important. So that's something you should consider for your narrative. There's also some practical limits. So the maximum number of lines that you can fit on a particular figure depends heavily on other context. If you need to plot lines with error margins or underlying scattered data, then you typically will only be able to comfortably fit 4 or 5 lines. Depending on how much overlap there is and how big the uncertainties are. For lines without error margins and no underlying scattered data, you can probably fit 8 to 10 independent curves of similar importance, as long as you use different line styles and different colors. If there's a lot of hierarchy and not a whole lot of overlap, you can get away with more. And if you have a lot of curves, but they evolve with a third variable, then what you can do is that you can use the little trick for selecting colors from a color map with a lens space argument, and then you can have a whole lot of curves and let the curves sort of fade out as they go to a particular value of a variable. And for an example, I used this plot here. So this is showing how you can pick lines out of a color map for a particular number of lines, and then you can pick a number of colors out of a color map to make your color palette, and then plot X number of lines, and then you can sort of use that to show a progression. So that's something you can get away with. And indeed, if anybody has been following, you've probably seen articles that use this technique if you've read any literature or news articles about how X year was the warmest year on record, and it will show a progression of temperature curves over the annual temperature curves for the past 20 or 30 years. And a lot of times they'll look like this, but probably in the reverse order. So typically they have the darker lines on top because the temperature is going up. All right, so with that, we've reached the end of this lecture block, and I will now take questions.
Actually, I just remembered one.
Yes?
Yeah. Is there a way that you can use a color map and remove the extremes? For example, like you don't want the very dark colors.
Yes, actually.
I don't know if...
Yes, let me go back a slide, because this is, well, if I can, there. So when you do this, when you use this lens space argument, what you can do is that you can vary these limits here, and where it lands, where along these limits you are working depends on how. Sorry, so the 0 here is the darkest value, and the 1 corresponds to the lightest. If you adjust these to fractions, then you're picking within a narrower range of the colors. So you don't necessarily get to, it's hard to super finely tune based on if you want a specific in color, but if you only care about the value, you can set that value here.
Yeah, that works. No, thanks.
Cool. Good question.
One small question.
Yes.
So these color maps that we have, they are all color blind friendly, isn't it? Like this plasma and whatever we feel here, like Viridis and
Yes, the well, the perceptually uniform color maps, yes, they are colorblind friendly because they are because they rely on no two values being the same. So and when I say value, I mean darkness. That's darkness or lightness. That's I'm used to using that as an art term. So the perceptually uniform maps were designed so that the whole color space would be monotonically increasing and from the dark to the light, and no two colors would match in value. So they are sort of ipso facto colorblind friendly.
okay, thank you.
There's also a Civitas color map that is specifically designed for the colorblind. Let me go back to this one. So yes, Civitas right here. This one is specifically designed to resemble the how it would look to perceive in with red-green, the most common type of color blindness, which is red-green blindness. It's essentially the same as Viridis, but washed out. So if you see all three colors, you don't have to sacrifice vibrance by picking Civitas. You can go with Viridis, and if someone is red-green colorblind, it will probably look like Civitas. So this last section is sort of a grab bag of do's and don'ts of data representation that I've accumulated over the years between me and previous advisors and colleagues who shared my passion for this kind of thing. So this one is more about tips and tricks of the trade, so to speak. So for most data types that I think that most of you will encounter, there's kind of a standard representation for those for most types of data. So for instance, time series, you typically have line stems, stack, or occasionally bar charts. Stat plots, if you've forgotten from the browser, or sort of like a stacked fill between, or like stacked histograms, that kind of thing. Probability distributions vary based on how many variables there are and what kinds of variables they are. So typically, if you're measuring within a single population, you have histograms or kernel density estimations, which if you don't know what those are, they sort of help get rid of the binning artifacts of histograms. If you've measured the same variable over multiple populations, you'll typically make a box or a violin plot. And I'll show an example of that of those in a little bit. And, well, and you also work a little bit with those in the last bit of the day 2 exercises. If you have a lot of variables that are correlated, you may use a corner plots, and I will show an example of that a little bit later in this talk. And this is especially true if you work with Markov chain Monte Carlo simulations, which those are for sampling or modeling the probability distributions of model parameters, assuming that it's the data the data are fixed and the models are uncertain. You have like budgets and fractions. You typically use proportional area charts. The pie chart is the most infamous, but it's falling out of favor, and we'll talk about that a little bit later, about why and what you should do instead. If you have vector fields, you typically use quiver or stream plots, unless you're in meteorology and doing the wind, in which case it might be WinBar plot, and there is a specialty plot for that in Matplotlib. If you've got spectra, you'll probably do lines of intensity versus frequency, wavelength or wave number. If you've got elevations or intensity maps, you might do contour maps, pseudo color images, surface plots. You get the gist now. And I just learned about volcano plots, which are basically apparently scatter plots on a similog axis. But I forget who brought it up, but it was nice to be made aware of that. So the main challenge that you're going to encounter when you're making plots for your research is how best to combine heterogeneous or different data types or sets for ease of comparison, or different data sets where you have like one main type that sort of fits a standard representation, but then you also have to put other stuff on top of it that doesn't necessarily fit that mold or doesn't fit the same mold as the main data type. And of course, there's how to make the key results easy to see and understand. And we addressed a lot of those, how to make data easy and clear and easy to see just from a purely visual standpoint, visual clarity standpoint in the previous lecture. But now we'll talk about how to sort of bring out your data or bring out the key results. So let's start with a do. Do distinguish your data if you're working on a communal plot. So by this I mean if you're adding data to a plot that other researchers contributed to, and that comes up repeatedly in different publications. So when adding data to that kind of figure, it is okay to de-emphasize other data and highlight what is yours or what is new. And you can do that with methods like decreasing the opacity or marker sizes of other data. You can show error bars only for your own data, which that is just a good idea for reducing clutter, and also because it may be that you only have the error bars for your own data. You don't necessarily know the ones for other data sets. It might help to color your data black and all other data lighter colors, or vice versa. You could use a really bright color for your own data and dull and neutral colors for the other data. And you can cycle through other data sets with a custom color cycler from the itertools.cycle module. And of course, you can emphasize, if you're working on a line plot with models, you can emphasize lines with thicker, darker, or more solid line styles, and then make other data have more widely spaced dashes or dots, light colors, things like that. Here's an example from my own research from a couple of years ago. So this was a plot from RLPITS 2021 using many of the previous data tips about data and markers. So our own data is in black, and the rest of the data are brightly colored. And we use the caption to label the data because there was too much to fit on a legend. That is an option. It's not the option. In hindsight, it's not the one that I would recommend. I would probably have tried to put them in a legend if I wasn't pressed for space. But this also shows you a way to how you can use the itertools cycle module. So here I've set up a cycle where you just enclose a list of things that you want to iterate over, and then you call next on that cycle variable. And then each time you plot each time you enter a new loop of an iteration, it triggers that next argument to execute. So here I've got a scatter plot where the colors and the marker styles are cycled through. And that's how and originally I had the markers and cycles, the markers and colors in the actual data table, but this is how you would do it if you had if you wanted to set up the cycles locally within your code. Now let's talk about, since we mentioned error bars and showing them only for your own plots, let's talk about error bars. you should all, hopefully it goes without saying for most of you in STEM that you're supposed to include error bars whenever it's feasible. And it's feasible it's feasible to do it on every point up to maybe a few tens of points. And it helps to include caps to distinguish these from markers. And also, if you have very small error bars along one dimension, sometimes the caps make them visible, whereas if you do like this style here in green, it may not be possible to see one of the along one of the dimensions that there is an error bar. Up to maybe 100 data points. If there are more data points, you may choose to omit the caps to reduce clutter, because if you have a lot of data points that are crossing each other, then the caps can resemble points. So if the caps intersect other lines, then that can look like extra points that aren't there. If you have hundreds of data points, then if they're on a line, you could use this error every quark of the error bar plot to only plot error bars on every nth point. If the data are scattered, this isn't such a good idea. If you have hundreds or thousands of data points, or data points that aren't on any sort of trend, then what you might want to do instead is choose a representative error bar in an unoccupied corner. And that you can do just by plotting a point that by just choosing coordinates in your system that are not really being occupied by data, and just plot a single point with the error bar function. And if you have lines, the main ways I've seen two ways of people representing the error margins on lines, and I have to say the one that is much better to understand is to use a light fill between. So you plot the error margins as lines that are filled between in a light color, and then plot the main line over top of that in a darker color. I've also seen separate upper and lower error margin lines that are just like lightly dotted lines that trace the main line. That's not as good of an idea, because sometimes those can be confused as separate models. One of the things that catches people off guard when they first start using the error bar function is that if you have limits, you still have to input a value for the X and Y errors if you want to show the arrow, because it needs a value for the arrow length. So a lot of times what you'll have to do is you'll have to read in your data and then use like a where expression to find the points where there's missing data, and then insert an appropriate fixed value for the length of the arrow to draw in the direction of that limit. This is a example for how I handled some error bars with some mock data. In the slideshow that has been saved, there's a separate slide that shows how I mocked up the data, because creating the limits and upper and lower error bars separately is not quite trivial. If there are asymmetric error bars, you have to have an n by 2 arrays, where the first subarray is the lower error bars, and the second subarray is the upper error bars. And then this first command here, the red error bars, those don't have any limits. So, and you can also see some examples of LaTeX here. The other error bar plot here is where I include upper limits and lower limits. So the up limits and low limits are for the y-axis. There are separate x up limbs and x low limbs for if you have limits along the x-axis. All right, let's talk about good and bad practices for rendering scattered data, because scattered data are some of the most common plots. If you've got a few tens to a few hundreds of data points, then as you already saw, it's a good habit to vary the color or marker style for different data sets or different values of a categorical parameter. That's something you can use to get more data on the same plot. And if feasible, you should always vary both colors and markers together so that the plots remain readable for people who are colorblind, or if it goes to print and ends up in black and white. But do keep in mind that some markers are hard to tell apart, as we discussed this morning. Don't color by a numerical third parameter unless it's correlated with at least one axis parameter. If it's correlated, it actually can be helpful to color scattered data if it is correlated with an axis parameter. But if it looks essentially random, then you're just adding extra noise that your audience has to interpret, and that's not a good practice unless it's specifically for different data sets. If you've got a few hundred to a few thousand data points, then it's a good idea to start including some transparency so that you can see where data are concentrated. Or alternatively, you can use the hist2d or hexbin functions, both of which are different versions of histograms. And if outliers are important, then it's a good idea to use logarithmic bin scaling. So when I say logarithmic bin scaling, that's sort of, that's what I mean is how they scaling the color of the bin by the log of the counts. So where outliers are important, typically the color maps will go from dark to light, and so if outliers are important, then they become very prominent in logarithmic with logarithmic binning, because then the background is white because it's undefined. So as I said, the way that you reduce scatter plot opacity is to use the alpha quard, which hopefully you've seen in at least one of the example problems by now. If you're going to use binning, there are a number of different binning rules, and you can pick the one that you should try multiple ones to see which one seems to fit the data best and make your point clearest. But generally, it's best to distribute a n number of data points over n squared to n to the cube root, or n to the square root to n to the cube root number of bins, rounded to the nearest whole number. And in this case, if you're looking at like a 2D plot or a 1D plot where the some of the bins are kind of out by their lonesome, the empty bins in between don't count towards the total tally. If you're doing a scatter plot, again, the distinct data sets can still be shown in different colors or as points or as line contours. However, you cannot overlay multiple histograms. So if you need to overlay two-dimensional data sets, then you're going to have to either use several contour plots or one histogram and the rest contours. And if you're tempted to contour a histogram, don't. I've tried it. It looks like a mess. You end up circling the boxes or the bins, and it creates all sorts of weird binning artifacts. So you don't want to do that. You have to resample your data to a regular grid and contour that. If you're working with many thousands of data points or more, then you're pretty much going to have to use histograms or contours. There's just no way to, after a certain amount of data, you're just not going to have the resolution to show the individual points. It just becomes too crowded and messy. In this case, it's a really good idea to learn about and use Gaussian kernel density estimations. So if you're not familiar with those, Gaussian KDEs are basically histograms smoothed by, what you're doing is that you're treating each data point as its own little bell curve with the unit height and width. And then you just sum over all of those bell curves. And then there's some variability depending on the width of the kernel that you choose and the shape of the kernel that you choose. There are other kernels besides Gaussian. You could use like a top hat function, which is, or a box function for different purposes. But most of the time, Gaussian is the one that you want to use, because then the resulting distribution is really nice and smooth, and it eliminates any binning artifacts. So it produces a nice continuous function that makes for nice smooth contours and nice smooth, and that allows you to make overlays of different contour data sets and have them be smooth enough that you can readily distinguish different ones of different colors. The big con of using, or the big drawback of trying to use Gaussian KDEs is that you need to either know Seaborn, which makes it very easy, or else if you, for some reason, can't or won't use Seaborn, then you have to use SciPy, and the process gets kind of tedious and tricky. And in both cases, the producing a Gaussian KDE requires quite a bit of processing time, considering the size of a given data set. And also, if you're using Seaborn, then contours can be overlaid and produce their own. And you'll have a legend produced for each set automatically. But without that, then you have to make your own something called a proxy artist, where you sort of create an extra set of, you sort of copy a line and a handle from the function, and then pass that manually to the legend function as a list of handles. So here's an example of what it looks like to make a Gaussian KDE plot with SciPy. And for this, I actually used some packages that were from, or a data set that actually comes built in as a test set for Seaborn, but I converted them to NumPy arrays so that you could see what it's like if you are starting from NumPy arrays. So you have to import Gaussian KDE from scipy.stats, compute a mesh grid for the X and Y coordinates to get the positions. And then you have to compute the Gaussian KDE for each one of these data sets, and then reshape and transpose the kernel results and plot them against, and then plot them against the X and Y grid. So you have to. It's a lot of. It's a surprising amount of computation, and I mean it's still small and doable, but this kernel function right here takes a surprising amount of time, even for a very modest data set. So these data sets here are of order 300 or 400 data points per set, and this can take upward close to a minute to process on a regular laptop. So if you have a very large data set, this can take quite a while. And then you have to append you have to create a list of lines, append lines append essentially empty lines of a specific color and label to this list, and then pass this list of lines to the legends handle, and then it will plot them. I should remember, I don't remember off the top of my head what these empties arguments represent, but you can find them in the documents because there is actually an example. There are other examples of proxy artists in the Matplotlib documentation. So over here on the upper right is what KDEs look like when they're made with Seaborn and the default color cycle. And you can also see the legend on the right. But the rest of this is this is kind of what a corner plot looks like, although true corner plots, you have to turn on this corner equals true argument in the pair plot or pair grid function in Seaborn in order to turn off the upper off diagonal plots. But why do that if you can use them for different helpful representations? So corner plots and pair plots for correlated variables are a very good idea. They make comparing different data sets very easy and also do a good job of representing the marginal along the y-axis and what's the word for the joint probability distribution functions on if you use KDEs on one of the off diagonals. But you can use scatter plots. You can use you can actually choose all sorts of different combinations of different plot types on the diagonals and off diagonals in this function. So corner plots and pair plots are great for showing correlated, for showing correlations between up to about 5-ish parameters. Can only really do a handful just because of the amount of space there is, but it's a great representation if you can use it. And it's, like I said, it's very easy to do if you've got the Seaborn package. The only drawback is that it can be hard to typeset because you have to manually override the access labels. Otherwise, they'll be labeled with the same variable name that you use in your code. There's also as an alternative that's specifically designed for Markov chain Monte Carlo simulations, you can use this corner.py package. You still have to install that externally, but it's easily installable with Conda or pip, and it's pure Matplotlib. So once you have it, there really shouldn't be anything else that you shouldn't have to worry about any other dependencies if you've got the rest of Matplotlib. The only drawback to the corner.py package is that some of the formatting is tricky to use. Now, of course, there are limitations to how many variables. As I mentioned, there's already limitations to how many variables that you can use corner and pair plots for. So you can't really do it for more than a handful of variables. If you've got more than a handful of numerical parameters, what you really want to use is a heat map of correlation coefficients specifically. That's not the only thing that heat map is for, but that I think is one of the best uses of the heat map. And you can use heat map to show the correlations between somewhere in the neighborhood of 10 to 30 numerical parameters. And there you're pretty much only limited by the minimum font size that's mandated by your journal. Of course, again, you should always err on the larger side. And also, you should generally ask yourself, do I really have to plot that many variables on one figure? Generally, if you've got that many parameters, there will sort of be groups of them that go together. And then it's better to sort of break them up and treat them separately if you can. But if you absolutely must, it is possible to use a heat map to show correlation coefficients or other or for other purposes. And there you have the choice of either a MShow with some boilerplate code that is included as a there is boilerplate code in the Matplotlib documentation for how to make a heat map using MShow. But again, there's a seaborn function that makes it much, much easier and more straightforward. And unlike most seaborn functions, the heat map function actually allows you to include an override for the typesetting of the X and Y row and column labels. So here's what this looks like for the seaborn map, the seaborn version, just because it was easier to show. The vast majority of this stuff up top in the coding section, almost all of that is just extracting the data and formatting the labels. The actual plotting point is just here in this this little green box down here. So I've taken computed the correlations, plugged that in as the main data frame, chose the color maps, turned on annotations. That's why there's text in all of these boxes. Given it X tick labels and Y tick labels manually, so that they actually look like they should in the paper versus how they look in your essentially a Python record array. Is what it looks like. It's what a data frame looks like. And then of course you can also control the formatting of the numbers and the aspect ratio of the chart. So this is a nice way to show correlations between many parameters if you have to. And this is sometimes a good thing to try when you're first exploring a huge amount of parameters and you're trying to identify what you need to group together and or what's just important in general. Because with this, you can look for the variables that are darker in color and just focus on those. And then the ones that are just where the correlations produce nothing but these sort of almost zero numbers, you can ignore those, or you can more or less ignore those relationships. So this is a good way to, if you're just starting out, figure out what variables you need to focus on in what combination. All right, moving on. Remember how I said pie charts are infamous? Here's a good reason. Many data science consultancy studies have produced, have shown that pie and donut charts are just not a good idea. First of all, they're inefficient. There's very little information for how much space they occupy. And more importantly, humans are much better at judging relative lengths than they are angles. So anything that's rectilinear is going to be better than a circular pie chart. Also, pie charts are easier to read when the categories are ordered by fractional size, but that might conflict with other orders that are better for actually finding a particular stat, like alphabetical, or if you have numerical bins, you might want to sort the bins in order of like size brackets. And then you could end up with pie charts where the slices are all different sizes and all different orders, and that just looks messy, and then it's hard to gauge how they compare. Also, usually the state of belonging is less important than what the actual quantities are. And probably most important of all is that inappropriate aggregation can obscure important category-specific details. And this doesn't just apply to pie charts, but it's something that you should consider if you're going to use something like that, if you're going to use proportional area charts. So just to give you a little demonstration, this is drawn from a data frame on survivorship of Titanic passengers by the sex of the passenger and the ticket class. So the This isn't quite an apples to apples comparison, but one of the key things to remember is that even if you're more focused on the raw counts, you can derive the percentages from these, but you can't go backwards, particularly not if all the percentages are muddled together like this, where you're getting the percentage of the total rather than the percentage of a particular group. And usually what you care about more about is the percentage of a particular group. And here with the stack plots, with these stacked bar charts, you can directly compare lengths and relative lengths and absolute lengths. So there's a couple of different ways to have rendered this data. So the one on the right is where I focused more on the raw numbers, and this example here on the right focused more on the percentages, assuming that since this is a binary, since the survival is sort of a binary thing, either they survived or they didn't, then you only really have to include the survival rate. Then you know immediately, what the death rate is. You just take the reciprocal. So this is the sample code for how I produce this bar chart. Figuring out the widths and offsets of bar charts that are grouped side by side is a little bit tricky, so that's why I didn't request it in the examples, but there are Matplotlib examples for multiple different amounts of groupings along the x-axis. So you can find that kind of boilerplate code. Other alternatives that are a good idea are waffle charts and tree maps. So I can show what those look like. Forget that. So a waffle chart, most of you have probably seen and just didn't know about it. It looks like this, where you have basically a certain number of either squares or meeples or figures of a car or something like that, and they each represent the same number of like a unit size or a unit quantity. So then you can sort of count up the number of these boxes and then multiply by the scaling factor for each individual box. Wow, this had a lot less ads on my other computer. And you can do that with, unfortunately, the only proportional area chart that is currently supported in Matplotlib, the only proportional area charts that are supported in Matplotlib are bar charts, pie charts, and stack plots. But PyWaffle and Squarify both are written in pure Python, so they're for external coding packages. They're relatively easy to install and run. So tree maps, you've probably seen if you've looked at news articles about shares of fossil fuels versus renewables, for instance. That's a common one that gets plotted. And a lot of times then you'll have each of these squares will then be subdivided by like countries or something like that. And there's lots of different ways you can format these. So I've included some links in the package that you can follow from the PDF if you're interested in those. Now let's talk about 3D plots. One of the things you have to consider with 3D plots is how depth is rendered. And not all 3D plot methods are equal when it comes to how depth is rendered for what type of data set. In general, I would say that the wireframe option is not very good for most things. If you give it some opacity, if you give it a little bit more opacity, it looks a little bit less ambiguous, but it's never quite as good as plot surface. And its main use case is if you have to put other data on top of it. But even that can be a bit problematic because if you have, for instance, scatter or spin plots, things like that, Matplotlib can figure out the ordering for data points within a single set, but once you start adding extra data, multiple data sets, it loses track. And then you can't even force it to get it right with Z order usually. Trust me, I've tried. This is what happens if you try to put a 0 point plane in the middle of a plot and then have points scattered around it. It just doesn't work. Matplotlib can't figure out the order between multiple data sets. Maybe one day this will be resolved, but for right now, it's not really workable. If you have to have a 3D scatter plots, it's probably best to try and stick with the with scatter, because at least that shows some opacity, or it varies the opacity a bit depending on where it's supposed to be in space. And then, but you still, in order to get a really good representation for it, you still kind of have to rotate it in space and have like an animated figure to work with. So these kinds of plots, you have to figure out where your the main challenge is finding the most interesting and relevant angle, and then showing that projection in your paper, or knowing when to take 2D projections and then save the 3D figure for an online interactive graphic. And speaking of manipulating things in 3D, there are ways that you can control. You don't have to just live with whatever orientation Matplotlib picks for you when you plot something in 3D. You can control that with the view init function, which you will play with just in a minute. So go ahead and get out your day 1 exercises and go to the bottom problem, because we'll have you play with that in a second. So with the view init function, what that allows you to do is set the elevation angle, the azimuthal angle, and the roll angle. And of course, then you set the vertical axis as either X, Y, or Z, so that that controls, that determines what elevation and azimuth do. But roll, I think, stays the same. So, so what elevation does, elevation rolls the figure along the horizontal axis in the plane of the image. Azimuth rotates about the vertical axis in the plane of the image, and roll rotates along the axis that points at you, points out of the plane. So, in order to get a little bit more experience with that, I would like you to pull up your day 1 exercises and go to the last problem. So that should be exercise number 5, if I recall correctly. Might be 6. Now I want you to, at the very least, set roll to 60 to see how that motion looks. From, for instance, the perspective of the solar system, in the plane of the solar system, because the exercise originally was to show the progress of the sun through the Milky Way for the past 66 million years from the Milky Way's perspective. But the solar system is inclined relative to the plane of the galaxy by 60 degrees. So this little roll is a handy way to see how that looks from, say, the perspective of the solar North Pole. So give that a try. I'll give you like a minute or two to find it. All right. So I'm going to go ahead and show what that looks like. If you plugged in the right roll value, it should have looked like this. If you played with any of the other values, that's perfectly fine. I encourage you to do so just to see what they do. They follow the right-hand rule. So it's the, if you're familiar with vectors, then you'll pretty much have a good idea of what the how you'll know what more or less what to expect when you plug in the values of elevation and azimuth. One more note on 3D plots. It is possible to do 3D vector fields, but I don't recommend it because right now Matplotlib is not doing a very good job of rendering those arrows. Each arrow is rendered with a separate line segment. I don't know why they do it this way as opposed to the way that it's done in 2D, which is where the arrows are actually a shape that comes to a sharp point and is rescaled appropriately. Whereas in 3D, it's just 3 line segments that often end up looking like cake pops when they're truncated like this. But right now it doesn't work well, especially if you try to color it or have a color gradient across the field, because what happens is that it ends up coloring different line segments different colors. And so then it becomes even harder to read. So let's wait for the developers to figure out polygonal arrows first in this type of plot. And one last thing when we're talking about making good plots, that is, be consistent throughout your paper. I've mentioned this before, that it's a good idea to stick with a consistent format and consistent fonts and consistent layouts and axis tick styles and all of that kind of stuff throughout your paper. At the very least, it's less distracting. So you want to set the tone and then stick with it so that your reader can focus on the results and not get distracted by differences between the images that are not due to the data. And one way that you can ensure consistency is by making use of the rcParams variable, and if you want to get more involved, use style files. So lots and lots of plot properties can be set internally by Matplotlib's default runtime configuration parameters or rcParams. And all of these are tunable. So you can tune subfigure formatting, like to adjust the horizontal and vertical space between subplots, for instance. You can control text and font formatting, sizes, font families, all that kind of stuff. You can control marker and line formatting. You can control color palettes, control default color maps. You can control axis tick configuration, so like whether they point in or out. Any and all of these can be set at runtime with dict-like syntax, or you can import them from files so that you can make sure that you're consistent across multiple papers. And you don't even have to think about it anymore. So the way that you can do that one way you can do that is with MPL style files. And I have an example. I haven't asked you to do any examples with this, but I have an example MPL style file in the that you can tinker with in the GitHub repository. So an MPL style file is a text file of key value pairs where each key is the RC parameter to modify. You don't have to include any parameters that you don't intend to modify. So the MPL style files can be as minimal or as maximal as you really want them to. So you can create and import a list of style sheets for different sets of rcParams. So you don't have to. So you can actually combine multiple style sheets. And there are also built-in style sheets that you can call by name without the full path from Matplotlib. So there's a colorblind style sheet, for instance. That's something that is built into Matplotlib and that you can import. And there are 2 ways to use style files. You can You can set it for the whole session by using plot.style.use and then the name or full path to your style file. Or if you just want it for one plot, you can use it in a with clause, which I will show you in just a second. So here I'm plotting the same plot two ways, one with the example style file that I mocked up with a custom color palette and color palette, grid style, and font size. All right, so first I'm plotting it with the with clause. So I create the figure instance, then with plot.style.context, the name of the style file. And then I plot the different plots on the same, different lines on the same plot. Go ahead and label the axes, and then plot.show. And that just keeps the settings for this one plot. And then if I try to make another figure with basically the same information after the with clause, then I just get the default parameters back. So it looks like this. So with the MPL style file, and then after the with clause. And that takes us to the end of today's lectures. So what all did we learn over the course of these 2 days? Well, hopefully what you take away from this is that there is a huge repository of options for creating and customizing your plots with Matplotlib. Hopefully you've learned why we typically use the explicit API, which is the ones where we use ax instead of like fig and ax instead of just plot. You've learned about customizing your axes, your grids, your fonts, and what you should pay attention to as far as colors and marker styles and things like that for accessibility. And we learned some other do's and don'ts of plotting for publication. So I hope you enjoyed this lecture series,